So anyway, the theme I'm going to do is quite a bit different. I talked about doing let me just go to the slide, which is the 4 Ds here. I took that and we talked about, could I talk about my science? But I thought really what it has more to do is to lead us into this discussion about what we need and so on. So I'm going to kind of outline some things that I think are high points. There's a lot of things I could have talked about on the 4 Ds, but these are the selection I have here. Now, those 2 guys there are there to remind me of something, which is that I'm in the process of coming to this, I missed the opportunity today to be with these 2 guys. I only see them a couple times a year. These are my 2 grandkids. Another theme that I'm an old guy. And the reason I point is I want to make that is not for sympathy, but just to say that I hope I have something to say. And I really did come here because I hope I can contribute to this discussion as we talk about for this afternoon. So anyway, here goes. That 24 years, that's a list. I'm not going to read them, but I've done almost a continuous set of passive array experiments over the last 24 years, starting back in the 1990 with the Joint Seismic Program. And so that's just to point out that, I've done this a lot. And so I want to talk about these topics. And the first thing I want to talk about, especially since we're on time issues here anyway, and I'm kind of maybe pushing this a little bit, but are the data desktop thing, because my point is going to be, if you read it at the beginning there, is that I sincerely believe that this is the biggest barrier to progress in the field right now, is problems we have with cyber infrastructure. And so I'm lumping data and desktop together, because that's my first statement, is that they are inseparable. The issue is how we take data and handle it and turn it into the products that are our papers. And there have been unbelievable changes in computing in the last 24 years, and every promise is that will continue in various ways. There's some numbers there, but I want to highlight this wonderful quote from David Hale that's in the PowerPoints you'll find for the US Array data processing workshops. Factors of 1,000 are hard on assumptions, and that is really, really true. And so one of the first lessons I want to point out here to everybody here, especially the young folks, these points here that are out here, which is basically that all kinds of computational things we have hidden assumptions. There are sometimes implicit things that the people who originally came up with the idea were burdened with 30 years ago that are often wrong. And if you look at some of the great advances we've been hearing about, and we all know about, or that came from US Array, a lot of them were people stepping back and saying, can I do that a different way? The noise tomography is a perfect example of something that was computationally not feasible, probably even 20 years ago. And now look at all the wonderful things that have come out of that. MT, I know, is another example. Most of MT modeling would be impossible without modern computational frameworks. So anyway, this is just an encouragement to everybody to always keep this in mind, that you have to think outside the box in terms of how things work and always question the underlying assumptions. The next one I want to talk about is this model, which is the long-standing, ever since the Rainbow proposal, vision of how data flows in IRIS, which is that you have data collectors, the list up there at the top, the TA, the GSN, and so on, the PASSCAL, and so on, flows into this thing we call the Data Management Center. Then the individuals out there at the end grab the data through the Data Management Center and work on it on your own desktop. That's the model we're talking about here, right? Data desktop, right? This is an opinion, but here's what I think about this. Since it's a core part of the facility, this part of the thing is working really well, has been for decades, of delivering data from the field sites to the Data Management Center. Unlike some fields, we don't have write-only systems, though, and we've got one of the great things about IRIS is the fact that this thing mostly works. The way data is delivered from the Data Management Center to us, although I will state that I think parts of it are kind of dated, and there's some advances that have been going forward, and we have to rethink this, I think, about the way we do this. And I didn't have time for it today. I left it out of, it was in my written words about this, but there are issues I think about. We have to rethink about the fact of data transmission rates in a high-performance computing system compared to data transmission rates receiving things from DMC. There are about 3 orders of magnitude difference in rates. And there's an example where how you get the data efficiently is a big deal. Anyway, I'm going to skip that one for now, but I mostly want to talk about this one, which is mostly broken. And that is that, I wanted to point out here that this is an opinion, but I also don't think it's based on something, and that is the experience from the US rate data processing courses for the last few years, and I can look at you and say, I really know what you guys do because I've had we've had most of your students here and know we've collected the best use policies, and it's broken. And the second part of the problem is not everybody in this room has worked with commercial seismic reflection processing systems. And if you've ever worked with one, you understand how broken it is and how different it could be. So here's my little image of that, which is the sort of a cutesy version of this anyway, is what we use is kind of like that. Whereas if I were using something like a reflection processing system, it's more like that. And one of the things we got to do is fix this. I think it's a really important thing for the advance of the field. Why? Well, here's some lists of some words. You can read that, and I never have given a talk, try to repeat the words I have, but it boils down to 2 big things. The university community is comparatively poor compared to the oil and gas world. And most of what we do is we're constantly changing everything. We're always tinkering with things. And so everything is research code that makes it intrinsically broken. Whereas in a petroleum shop, time is money, and there's a lot of money behind it. So you have such a contrast between the kinds of packages that exist for the specialized problem of reflection processing relative to some more generic mix of diverse things that we do that is really problematic. But that doesn't mean, so anyway, I think a key assertion here is that I really think the cyber infrastructure is the problem totally comparable to what formed IRIS in 1980 for instrumentation. And that is that everything is fragmented. There is no community consensus on the way things should go, and it messed up the science. And just look what happened is when we came together to make the IRIS consortium over the last few years, over these years. So that last point is really true. I really sincerely believe that is the largest bottleneck to progress we have in the field right now. So what do we do? Quick, I'll go through these. I think the key is of defining some processing framework that can be the core of a community development for a seismological generic processing system that's open source, that everyone contributes to as a community development effort. There are lots of ways to make that happen today. Everything is in place to do it. Here are some properties I think it needs to have to make this work. But we just need to move on with it. So how do we do this? Well, here's some statements. I think we got to stop talking about it and actually do something about it. And I don't think that it's like we have to start somewhere and then it'll build itself. I will point out that EarthCube is not solving this problem. I've been to lots of EarthCube workshops and know that that's not what this is going to be. This is a seismology problem. It is our domain's problem to fix this problem. And we need to get started on it by forming a group or whatever to get action on the problem. Okay, and now something different. Now to dirt. Originally I had it dirt in the same order, but I was passionate about that topic. I wanted to talk about it. I sort of 2 topics on the dirt topic I want to talk about. First is telemetry. I think that everyone in this community needs to recognize the importance of IRIS in the development of modern telemetry systems. And this is a history timeline here, which is that, in the old days when I was a student, where everything we used, in fact, that stuff is still out there, analog telemetry, that's what the red line shows. But the digital era in seismology began really with AMSA in the early 80s. And there's been a series of technological developments there that led to the TA being what it is. And especially for those who haven't seen this history, should realize that it did not come, the 99%, over 99% data recovery rate of the TA did not come from a vacuum. That was a long development that was really centered around a program which at the time was kind of controversial called the Joint Seismic Program. But the TA is the legacy, actually, of the IRIS Joint Seismic Program in many, many ways. So I guess this is just repeating what I just said in words. But and I also think it's just important for us to recognize that leadership that has occurred here. And the last point that I didn't point out there is that this will continue, I think, which is that the way we will always move forward as the way we move forward in this rotation is opportunists. We're a small field, we don't create new technologies. What we do is exploit them at the time that they came. And a lot of the developments that led to the TA were based on just that principle. So a lot of you have seen things like this. I just want to do some quick examples where things I will show you about. I'm not going to read these, but a lot of people have talked about these kind of things before, about what is the good and bad things about telemetry. The big thing is that the data quality is inevitable about what the advantage of doing this. And it actually saves money in the long run for many kinds of experiments. It's not for everything. There are many cases where that's not the thing, but it's definitely, because it does add complexity. Probably one of the biggest problems is that last point on the negative is that there is an additional background that's needed to be able to do this. And there is a larger energy barrier to initiating an experiment with telemetry. I want to quickly talk about OINT, the project we have going, FA experiment we have going on right now, because I think it's an illustration of some of this in terms of the advantage of telemetry. This just illustrates where we've been in southern Illinois, Missouri, Indiana, and Kentucky. The red dots are where we are right now. We have really good cell coverage, most of that area. For most of the time, we've had 51 to 55 stations at different times running telemetry. And the fact of the matter is, you can demonstrate that we have stations we use with telemetry, we have TA data recovery rates, better than 99% data recovery. It's not 99% good data, however, due to an obnoxious problem with high failure rates of sensors, which is a different issue we need to talk about, probably in terms of going forward. But with those problems have improved the data quality enormously because we saw them right away. They didn't sit for 3 months, and you don't have nothing off the station. So they were fixed within days instead of months. And that's so that the quality amount of good data is inevitable. If you pay attention to the data and actually work with it, telemetry is a data quality gem. It also saved us a ton of money, more so because FA paid the bills for the cell phones. But if I sent around the Woodward thing, we would have saved money even if we had paid the cell phone bills, because of the amount of time spent doing data service runs to pull instruments off RT-130s every 3 months. You have to go there at least in a standalone station, and you can reduce that interval you could do it for a year if you didn't have the limitation on the recording media for a 130. Okay, well, I'm going to move on. I'm going to quickly cover this other dirt issue, which is the vault construction. I'm going to blow by this pretty quick because a lot of this is pretty well known, but I want to make sure it's partly an educational thing. to go by a history here that I want to talk about. There's just quickly here, this is OINT data along an east-west profile. It's like, that's 30 days of data, and you see the daytime periods very clearly. If you go to 3 days, it's even clearer. You can see the individual, these are all horizontal components. What happens, you get very strong amplification of noise on the horizontals relative to the vertical. And we actually were fortunate enough, part of the experiment here this winter, we put in the first set of trillium post holes. And if I hadn't told you, you wouldn't know the difference. So the data quality, this data quality is going to be an issue for anything. Horizontal noise is going to always be high. And why is that? Well, we've known this for a long time. We totally understand this, and that is that long period noise like this is dominated by tilt on the sensor. When you put something in dirt, it's going to move around. And I want to point out that this is an unbelievably old, unsolved problem. This was what happened when the first time I really worked with David was back in 1990 when I was on sabbatical at Lamont, and this picture was there. And we actually did some of the first tests like this. It was like totally evil. It's like, I can't do this. Put this first set of STS-2s they had in a bag and throw it in the dirt, right? We waited to make sure it wasn't going to rain or something. But anyway, since then, it's been totally known. It was known even before that. Other tests that had shown this, the problem of putting a broadband sensor in dirt. And I'm just going to breeze through some. There are a whole lot of examples. I don't want to waste time on this. Of about how various ways people did this over the years. I'm going to just go through this, but there's a tip. There's one of our stations right now, but the key thing is when you have something like this, a FA vault in particular, is no different than sticking a sensor in the dirt. It's just that the container is only there to help you keep it from getting ground and save the instrument. And so some things we sort of know empirically is that, and I've seen over the last 24 years doing this kind of stuff, is nothing can beat a rock site where you can put the instrument on this rock pad. Even if it's in a mine, you can't beat that at all. But if you if you get the sensor down to bare dirt and lay a concrete pad on the bedrock, you really have a quiet site no matter what you do. It's when you put them in the dirt, all kinds of bad things happen, and in those sites, the devil is in the detail. And my assertion is we don't understand why. And so I would assert that we definitely have what we know is that that dirt is unstable. And there are lots of processes that tilt that thing, do this, but we don't really know which one dominates. And every site is totally trial and error. And came up in a big issue yesterday, talk about the TA in Alaska. It's like, how much are you going to spend to buy 15, 20 dB of horizontal long period noise by taking a drill rig out to make sure that you got the sensor stuck into hard rock. But we don't really know what to fix problems, what really causes problems like that, in my opinion. So I will quickly just mention this, and I'm going to blow by it, which is that I'll just make the statement, which is that another thing that's important has happened in 24 years in dissemination is the area of 3D visualization. This is an example from circa 1990s where the hardware to do this particular thing cost $50,000. And it wasn't, and the hardware and software systems to do this at that time were not common. This little thing shows particle motions for the Bolivian earthquake all across the state of California. Talk about what it says, but I want to go on. Here's a newer version I did for a paper that's in Geosphere, which is, where's my thing? showing the geometry of multiple things in 3 dimensions for the geometry of the subduction system in Alaska. And I did that on a $1,000 piece of hardware and software. So the point being that in dissemination, there is no excuse any longer other than educational issues of using 3D visualization techniques as part of your presentations and as part of your publications, because all journals are electronic pretty much now, and we need to start using them more consistently in the way we do things. And there is my summary, repeating what I had in the first word, and I will stop there and try to ask questions for everybody.